Okay, good morning, everybody. Today my plan is actually to finish discussing integration of some powers of trigonometric functions. But have you finished talking about the next technique, which is trigonometric substitution? Because if I remember it right, you said you started with it last meeting. So were you able to finish it today and start with integration by partial fraction decomposition? So if that's the case, then we should pick up the pace. But just let me know if you finish 8.3. Okay, that's good. So we can take our time and probably today focus on 8.2, and then towards the end probably start with 8.3 or start 8.3 on Monday. Okay. So last time we started talking about some general methods or guidelines in integrating some powers of trig functions. But I guess here, I guess Arsalan is, well, is asking about how to distinguish how to determine what method to use when solving certain problems. Like I guess you have it in the end of the electronic homework. So maybe I can start with that. Okay, so I hope by now it is clear when you can use U substitution. When you're doing U substitution, the only requirement is that you rename one of the functions involved and call it by another variable, and it will work as long as you get the appropriate du. So okay. So and actually that's the first thing that you can try. Imagine probably doing things in your head first, trying to let u be equal to one of the functions involved, and then um, compute the du. And if you can find that du from the original given integral, then you're good. You can do u substitution. But if that won't work, the next thing that you can try is integration by parts. This is commonly used whenever you have a product inside your integral. And this will work if you can find or if you can choose a function u that is easily differentiable and a function dv that is easily integrable, right? And then sometimes it will fail. So you go to the third technique, which is integrating trigonometric powers. And as the name implies, we only use this whenever we have combinations of trig powers. So to answer Arsalan, maybe I can give you some hints on the last portion of the electronic homework. So I guess one of the problems there was x squared sine of x cubed dx. So here, your candidate for the function u, if you're trying to do u substitution, is to let u be equal to 3x squared. Let u be equal to x cubed, right? So if you let u to be x cubed, you know that what you need for the u substitution will work is to have du equal to 3x squared dx. And if you can find at least the literal part or the variable part in your integral, then u substitution will work. And I guess here, u substitution will work perfectly fine. Okay. But if you are dealing with problems like, say, x squared sine of x dx, here you cannot use any u substitution because there's no point of letting u be equal to x, which is the function inside sine. It won't change anything in the problem. You cannot let u to be equal to sine of x because that will require a cosine for the du, okay? And you cannot let u be equal to x squared because you will have a sine x still remaining. So that means this is not solvable by u substitution. So your next bet is to use integration by parts. And you see that it will work because you can pick x squared to be your u. And remember, what do we do with u? If you have a function u, you take its derivative, right, in the integration by parts routine. So, but if you differentiate x squared, you get 2x. Differentiate another time, you get 2. You differentiate another time, 0. So that means x squared will eventually be differentiated to 0 after a couple of steps or 3 or 4 steps, right? So that means that's a good choice for u. And sine x dx is a good choice for dv because you can easily integrate sine of x, right? Because it's an elementary form. So that means here integration by parts will work. Okay. And then I guess you also have sine of x squared dx. Here, if you try u substitution, your only candidate is to let u to be equal to x squared. But if you do so, then du will be equal to 2x dx. But you obviously don't have a 2x dx in your integral, right? So that means u substitution will not work here. Integration by parts. I'm not sure if integration by parts will work here. Maybe we can take a look at it. So your only choice is to take u to be equal to sine of x squared, because you cannot choose that to be your dv because you are required to integrate it. So our dv will be lonely x. And then here we'll have du equals 2x sine of x squared dx. And then v is equal to x. So this guy will be uv minus integral of v du, so it's x sine of x squared minus integral of v du x 2 times x. So I'll have this. Okay, and then here, I guess here you will have, you can try, you cannot do u substitution. You'll need to do integration by parts. But the problem with integration by parts here is we will have the integral of sine x squared once more. So I guess if I'm not mistaken, this integral is not of an elementary form, meaning there's no way you can integrate this exactly. Let me just double check if that's the integral that I was thinking.
To integrate that, wouldn't you put u equals x to the square? So that way it's du equals 2x?
Well, yeah, you can do that, but if you will let u to be equal to x squared, then you're right, du is 2x dx. But my problem here, or my reservation, is that I have a 2x squared. So basically, I can take 2x to be my du, but I have an x still remaining, right? So I guess here you'll need a fancy integration technique, which we call the Fresnel integral, but that's beyond undergraduate level. So I guess your answer here is none of the above, because this is not an elementary form, and without knowledge of those Fresnel integrals, you cannot solve this. And then in the homework, you also have integral of e to the x squared. This one actually is not solvable by hand, or actually not solvable at all without the use of infinite series. So this is not an integrable form. So you see, this is a very basic function. If you think about it, it's the integral of e to the x squared. It seems very simple, right? But unfortunately, this is not in elementary form. Actually, it's not integrable unless you will go into the realm of complex numbers, right? So I guess this is also beyond the coverage of the course. Even I think undergraduate mathematics major cannot solve this without using or cannot solve this, or we are not teaching undergraduates how to deal with this one, because this will involve the imaginary error function, which is high-level mathematics. So here, none of the above. You cannot use any of those basic integration techniques that we will be discussing. Okay. Then you also have x e to the x squared dx. I guess this is fine. This is easier, ironically, than the previous one, though it has an extra x in there. But you see, you will need that extra x for the u substitution, right? Here you can let u to be equal to x squared, then the du will be 2x dx. You're perfectly fine, okay? And then the last problem is cosine squared x dx. This is a power of trig functions, which perhaps you can solve later. Or have you solved this in the lecture already? Cosine squared x? I hope you haven't, so that I will have an easy example for even powers of sines and cosines. Okay, so I guess I should give you a more complicated example. But Yeah, I hope this helps you with the rest of the electronic homework. But actually, you need this. You need to develop this kind of pre-analysis before you dive in solving a certain problem. Because the thing is, in the exam, I don't remember exactly, but I guess you will be given some integrals and you will not be told what technique to use. And I guess a good chunk of the time will be required for you to determine what method to use. So I hope by now you're starting to get a feel of what method can or will not work, so you can try. So you have an idea of what method might work before really you're writing something, because you might end up trying a method that will not work, and you have wasted a good portion of the time for the exam. Okay, right. So let's go back to our. So I won't include this in what I'll upload. So delete page. So I hope you you listen there. Okay, because that's part of your e-homework. Okay, so we're doing powers of trig functions, and I guess we have identified what to do for powers of sines and cosines. If either of them is odd, what you can do is to reserve a factor from the odd power and then write everything in terms of the other trig function, right? Using the Pythagorean identity sine squared x plus cosine squared x equals 1. And all other cases, that means both of them are even, then you need to use the half angle identities. But before trying to do these fancy techniques here, sometimes you will be required to just apply some basic trigonometric identities, which is a good reminder that you need to go back to trig or pre-calculus notes to see what are these identities that you can apply, right? So maybe let's start with those things that doesn't really require fancy substitution techniques. Just straightforward trigonometric identities will work. Let me see. Maybe I'll start with problem. Let's try problem 21. And again, kindly let me know if you have answered some of the problems here in the lecture, so that we won't be repeating your solutions there, right? So this looks complicated, but um, obviously this is not a power yet of trigonometric functions, but a good exercise is to recall those trigonometric identities. And one difficulty for some of the problems here in the worksheet is that some of the trig functions doesn't have the same arguments, right? So on top you have x's inside your sines and secant, but in the denominator, you have 2x inside your sine function. So it is almost impossible to integrate if you have different arguments for your trig functions. So I guess, or I suggest the first thing you try to do is to write them in terms of a single argument, right? So here, we need to apply the trig identity for sine of 2x, and hopefully you still remember it. So I'll copy the numerator. Sine 2x is equal to 2 times sine x cosine x. That's your trig identity. And then here, let's see what can we do. So I can cancel the sign here and the sign there. So we'll be left with the integral. I'll take the 1/2 out of the integral. And then I'll have a secant x over cosine x dx. But again, if you'll try u substitution, nothing seems to be nothing will work. So try another trig identity. Remember, 1 over cosine is exactly secant. So basically, this is just 1/2 secant squared x dx. And it is elementary in form because we have a formula for the integral of secant squared, which is tangent of x. And then just put the arbitrary constant c. So here, nothing fancy, but we just need to recall those trig identities that you have learned in previous classes, right? And I think now it's becoming more apparent that really math is a very sequential subject, meaning you need to remember at least the basics from previous courses. All right. Let me try another one. let's try. Have you tried answering some of these? Just let me know if you have if you notice some interesting problems. Probably I'll try 31. Okay, so for problem 31, we want to integrate cosine 4x sine 2x. Again, one problem here is that we have different arguments. The cosine has a 4x inside it, while sine has a 2x. So again, I'll try to write it in terms of a single, I'll write this so that they will have the same argument. So for that, I'll recall that cosine 4x can be written using the double angle identity. So I can write it as, perhaps I can write it in terms of sines. So I can write it as, should I write it in terms of sines? Yeah, I'm thinking what would be the best substitute here. Well, yeah, I can try writing it as 1 minus, actually, I can write it in terms of cosine. So I'll write it as 2 cosine squared of 2x minus 1. Right. So from your double angle identity. Okay. And then now, okay, I'll use this identity here to convert the cosine 4x. So I'll have 2 cosine squared 2x minus 1 times sine 2x dx. And what I like about this form is that all of the trig functions has a 2x inside of them. So we can perform probably u substitution here. So now we can let u to be equal to cosine 2x. So du becomes negative sine of 2x times 2 dx, right? So that means here I need to have negative 1/2 because dx would be, sine 2x dx will be equal to negative d over 2. So I'll have a negative 1/2 in front, integral of 2u squared minus 1 and then du. Yeah, I'm trying hard to keep a straight face on because I'm reading the chat on the side. But anyway, hopefully I did the calculations right here. Okay. So now we can integrate. So this would be negative 1/2 2u cubed over 3. Oops, I'm integrating already. That should have been a grouping symbol. Minus u plus the arbitrary constant c. Okay, is this fine? I guess so. And then you can just carry on with the simplification. So this would be negative u cubed over 3 plus u over 2 plus the arbitrary constant c. And then we need to revert to the original variable. So this would be negative cosine cubed 2x over 3 plus cosine 2x over 2 plus the arbitrary constant c. Okay, guys, do you agree with the solution? And here you see the utility of those trig identities. Okay. Okay, I was thinking doing problem 30. Let me see. Yeah, problem 30 looks interesting, though I guess here there would be a lot of manipulations. So perhaps I'll just start the solution and let you finish it later. Because if you think of it, these are off tangents with the topic because I'm not really working with powers. I'm just manipulating the trig identities in order for u substitution to work, which is basically the same thing as what I have written earlier. What's the point of integrating trigonometric powers? But these few examples that we started with are just showing off the utility of using trigonometric identities. So this one is a little bit hard because here we have a sine 2x and a cosine 3x. So what I can do here is to use identity for sine 2x. It's 2 sine x cosine x. And then cosine 3x, I will use the, what do you call this, the sum identity. Maybe I should do it step by step here. I'll write it as, oops. I can write it as cosine of 2x plus x dx, right? And there you can see I can use the sum identity. So this would be cosine 2x cosine x minus sine of 2x sine x dx. All right. So if you remember that, that's the addition identity for cosine. Okay. And then write everything in terms of the argument x alone. So you see that cosine 2x can be written as, that's the thing about this problem, because cosine 2x has 3 expansions. So I guess the more useful one is to write cosine 2x again as 2 cosine squared x minus 1. Then we'll have a cosine x over here. Minus sine 2x again is 2 sine x cosine x sine x dx. Hopefully I don't miss any trig identity here. Okay. And then my strategy here is to see if I can write, I can write everything in terms of cosines except for this factor, because I'm hoping that this factor together with dx will be my du, right? So essentially my goal is to let u be equal to cosine x, and then I'm reserving that sine x dx to be my du, right? So that means, aside from that, I should not see any signs anymore, right? So where can I have a sign left? If you look at this factor, there would be a sine x here and a sine x here, but that's a good thing because when you multiply, that's going to be sine squared, and I can write sine squared using Pythagorean identity as 1 minus cosine squared. And then I can do the u substitution, right? So here, I'll write this as, probably I'll put the 2 out of the integral. That's a common factor. And then I'll have a sine x over here. And then we'll have, I'll multiply everything by this cosine x inside. So I'll have 2 cosine to the 4th x minus 2 cosine x, oops, cosine squared x times sine squared x dx. So kindly double check this. Let me see. 2 cosine to the 4th minus cosine cosine squared minus 2 cosine squared sine squared. Okay, I think this is fine. And then I'll have a sine x, and then 2 cosine to the 4th x minus cosine squared x minus 2 cosine squared x times 1 minus, oops, cosine squared x there. So you see I use Pythagorean identity here. Dx. All right. And then now I can let u to be equal to cosine x. Then that means du is negative sine x dx. As I intended, that's why I reserved that sine x over there. So we'll have negative 2 over here, because du is negative sine x dx. So we'll have integral of 2u to the 4th minus u squared. And then I'll have a minus 2u squared plus 2u to the 4th du, right? And then we'll have -2 integral of 4u to the 4th minus 3u squared du. And so this is -2 times 4u to the 5th over 5 minus u cubed plus the arbitrary constant c. Then we just need to revert to the original variable and carry out some of the arithmetic here. We'll have -8 over 5 of cosine to the 5th x plus 2 cosine cubed x plus c. Okay, that's the long one, but nothing fancy. We just played with those trigonometric identities so that we can end up with a nice U substitution. All right, any questions with that? I know that's a long one, but I hope the process is clear. Okay, are you guys still with me? I hope you still are. Let me see. Let's try another problem. Let's see. Which one is good? Yeah, Herson, you're correct. Time to review those trig identities because you will really need them here. Let me see. I guess I wrote some of the nice problems here. Oh, let's try problem 33. Okay, so for problem 33, you see here that you have an even power of, you have an odd power for cosine. Remember, the first thing that I wrote here on top of our worksheet is the general guidelines for powers of sines and cosine. So the first case is either m or n is odd. So it's sufficient to see at least one of those powers to be odd. And then you're in a good shape. What you need to do, isolate one factor from that odd power and reserve that for your du. And then write the remaining power using the Pythagorean identity. Then you'll be good. The other case is when both are even, then that's when we will use this this half angle identity over here. Okay, so but if you look at problem 33, so here I have a sine to the 3/2 x. 3/2 is neither odd or even, so it's neither odd nor even. So that means we rely on what happens to the power of cosine. And luckily, the power of cosine here is odd. Remember, case number 1, we only need one of them to have an odd power, right? So luckily here, cosine has an odd power. So we'll follow the guidelines I set earlier. So you copy the other function, and then from the odd power, you reserve 1. We are reserving this to be our du for later. And then what remains here is cosine squared x, right? And then that's the beauty of having an odd power, because once you isolate one of those factors, then you will be left with an even power for cosine, right? And you can use Pythagorean identity for that and write it in terms of sine. So you'll have 1 minus sine squared x cosine x dx. And here we can let now u be equal to sine x, because remember our reserved factor for the du is cosine x dx. So it's time for us to take advantage of that reservation we did. So du is cosine x dx. So the integral now becomes u to the 3/2 times 1 minus u squared times du, which is now an algebraic function. So you can have it as u to the 3/2 minus u to the 7/2 du. And then we can integrate. So we'll have u to the 5/2 all over 5/2 minus u to the 9/2 all over 9/2 plus c. Okay. And then we'll have 2/5 u to the 5 halves, but u is sine x, so we'll have this minus 2/9 sine to the 9 halves of x plus the arbitrary constant c. All right. Okay, so that's what you do whenever you see an odd power in your problems, right? Actually, it's easier than having to deal with both of them being even. So let me see if we have an example for that here. I was hoping I can give you a cosine squared of x, but I guess you mentioned that you might have probably solved that in class. So I cannot do problem 16. Should I invent something out of the blue? Well, we can try. Hopefully, we can solve this. Because one problem about integration is that not all functions are integrable. And at this point, we only have limited techniques. So I'm praying that this example can easily be solved. But this is just sine squared x, cosine squared x. I'll keep it simple so that yeah, so that I can illustrate the process here. So you see here that both of them are even. So we cannot do the same technique as what we did before, because when you isolate one of the powers from either of these two factors, you'll be left with an even power, and you cannot use the Pythagorean identity for that, right? And as I mentioned above, this is case number 2, which basically requires us to write this trig functions in terms of the half angle identities. So sine squared x, if you recall, is 1 minus cosine of 2x all over 2. And then cosine squared x is 1 plus cosine of 2x all over 2 dx. So this is an application of the half angle identities from trig. I also wrote it at the beginning of the worksheet, so in case you want to review this. And I guess this is the only way to go when both of them are even. So you don't have any choice but to remember this. And then we simplify the integrand and see what we can get. So I can take the 1/4 out of the integral just to make things easier here. Then I'll have a 1 minus cosine squared 2x when I multiply the tops. And then all multiplied by dx. All right. And then luckily here, I still have an even power for cosine. But the good thing is I can use Pythagorean identity here first. So I can write it as 1/4, oops, of integral of sine squared 2x dx. But unfortunately, this guy still has an even power for sine. And again, you have an even power for sine, we need to use half angle identities again. So another application of the half angle identity will give us a 1/4 integral of 1 minus cosine of 4x all over 2 dx. Again, this is by half angle identity, because remember that sine squared of 2 theta is equal to 1 minus cosine of, this is a single theta, 1 minus cosine of 2 theta all over 2, right? Now, I have sine 2x here, so that means that's my theta. So here, for the cosine, I need twice the theta. Our theta is 2x, so twice of that is 4x. That's why I got this, okay? And then I can take the 1/2 out again. And then we'll have 1 minus cosine of 4x dx. And then for this, I can let u to be equal to 4x. du is 4 dx. So that means dx is the same as du over 4. So this dx here will be replaced by du over 4. So I can put the 4 outside the integral, and we'll have 1 minus cosine u du. So we'll have 1 over 32. The integral of 1 is u. Integral of negative cosine is negative sine u plus the arbitrary constant c. And then we revert to the original variable. So this is 4x minus sine of 4x plus c. Okay, so that's what you do whenever you don't have an when you don't have an odd power. Okay, all clear? I'm hesitant to ask if everything is clear because usually students forget their trig identities once they graduate from algebra, thinking that they will not meet them again. But here we are using trig identities almost in all of the problems that we have dealt with. Okay. Any questions on the process? Because it's up to you to review the trig identities, but I hope the process makes sense. Now I'm a bit nervous about your silence. Yeah, good to know, Harrison. So you still have time to review these trig identities. You don't need them all, but at least the basic ones. The Pythagorean identity, the half angle identity, the sum and product identities. So yeah. Okay, if that's fine, I hope you take time to practice some of the practice using this worksheet because that will be a nice way to recall this trig identities. Okay. Now, it's as if that is not enough. I'll throw in another cases which will require, or another case which will require some more trig identities. Okay. So now what happens when you have combinations of secants and tangents in your integrand? But as a consolation, this process also holds if you have a combination of powers of cosecants and cotangent. So the cases or the subcases are analogous to each other. So let's see what are the cases here. But you see that there's nothing new here. Basically, we are trying to take advantage of trigonometric identities in order to have a good U substitution. So first case, or first subcase, when m is even. M is the power of secant. So if the power of secant is even, what you need to do is to reserve a secant squared dx for du. Okay. Okay. Why is that helpful? If you reserve a secant squared from an even power of secant, then you will be left with still an even power for secant, right? And the utility of that, you can use this identity that even power of secant can be expressed in terms of tangents. So you can write secant squared x as 1 plus tangent squared x. And in your solution, all the remaining factors will be in terms of tangent. So you can let u be equal to tangent x and use secant squared for the du. And that's why I reserved secant squared x from the even power of secant. Other case is that when n is odd and m is greater than 1. If you have an even power for tangent and there is at least 2 powers of secant, then what you can do is to reserve a secant x tangent x for du. Could also include the dx there. Okay. And you can guess what I am trying to do here. So if I'm reserving a secant x tangent x dx for the du, then I am planning to let u be equal to secant, right? So that means everything should be written in terms of a secant. But that's a good thing because remember, I assume that n is odd. If I take one of those tangents for the dx, then I will have an even power of tangent left, right? So if I have an even power of tangent left, then I can use this identity. The tangent squared x is secant squared x minus 1, and the remaining parts of the integral will be expressed entirely in terms of in terms of secants. So basically, I can let u to be equal to secant x, and luckily we have reserved a secant x tangent x for the du. So that's what you can do. But this is the bad thing. All other cases, we don't have any clear guidelines. So no guidelines. So you need to figure out ad hoc for yourselves what can happen for all other cases. Mostly, you can use IBP or integration by parts for all other cases, but it is not a guarantee that you can find an answer using IBP. Okay, so that's the only unfortunate thing about this. So let's see some examples. Let me try problem 27. Oops. Okay, so for problem 27, we see here that the power of secant is even, so it will fall under the first bullet I wrote earlier. So here I will reserve a secant squared. For my du, right? So that's reserved for the du. I can do that because the remaining even power for secant can be expressed in terms of the tangent identity, right? Using the Pythagorean identity. So here I'll have tangent to the fourth pi x, and then secant squared is 1 plus tangent squared of pi x times secant squared pi x dx, right? Then now I can do the u substitution. I can let u be equal to tangent of pi x. That means du is secant squared pi x dx times pi, right, by the chain rule. So we'll have a 1 over pi outside times integral of u to the fourth times 1 plus u squared du, as we planned. And then here we'll have 1 over pi. Then we'll have integral of u to the fourth, which is u to the fifth all over 5, plus the integral of u to the sixth, which is u to the seventh over 7, plus the arbitrary constant c. And now we can revert to the original variables. So we have 1 over pi times 1/5 tangent to the fifth of pi x plus 1 over 7th tangent to the 7th of pi x plus c. All right. So you can try problem 24, exactly the same thing, because there you also have an even power for tangents. Now, let me see another one. Let's try problem 28 or 26. Let's try 26. Okay, for problem 26, you see that the power of tangent or the power of cotangent is odd, and cosecant has a power greater than 1. So this will fall under bullet number 2. So for bullet number 2, the suggestion was to isolate a cosecant cotangent for the du. So that will leave us with a cosecant squared and a cotangent squared here. And then our reserved factor for the du was cosecant x, cotangent x, dx, right? So this is what I reserve for the du. And with that in mind, I am planning to let u be equal to cosecant x. So that means everything left should be expressed in terms of cosecant. But that's not the problem, because here I can have a cosecant squared x here. Cotangent squared is cosecant squared x minus 1. And then this would be still cosecant x, cotangent x dx. All right. And then here I will let u be equal to cosecant x. And as planned, du will involve cosecant x, cotangent x dx, but with a negative sign. So the integral now becomes negative of integral of u squared minus 1 du. That would be negative of u to the 5th over 5 minus u cubed over 3 plus the arbitrary constant c. And then let's revert to the original variable. So I can write it as cosecant cubed x over 3 minus cosecant to the 5th x all over 5 plus c. Okay. So basically, these things will just require you to really play with identities and identify what is the right case. Okay, so as long as you remember the cases, or at least you know the gist of the case, then you're good. Of course, with the prerequisite of knowing the identities. All right. Okay, now somebody asked me this from one of my CASA tutorials, and I guess I think this is one that appears in your online quizzes. That's a tangent to the 5th of tangent to the 5th of 9x dx. Okay, so here this will not fall under any of the first two bullets, because here you have an odd power for the tangent, but there is no secants involved. So this will fall under the third bullet, wherein we don't have any hard guidelines. So for this thing, I will try to use integration by parts. Okay, so what will happen first is, well, I can try to have a secant over here. So I can write it as, I guess the only way is to have a tangent cubed of 9x here versus a tangent squared 9x here dx. And then write this thing in terms of secant. So I will have a secant to play with, because tangent alone is hard to evaluate. So I'll have here tangent squared is secant squared x minus 1 dx, right? So now I will have integral of tangent cubed 9x secant squared 9x minus tangent cubed 9x dx. Actually, here I think I don't need to use integration by parts, just successive use of the identity for tangent squared, right? So because here in the first integral, so I can split this into two. Okay, so in the first integral, we can let u be equal to a tangent tangent 9x, and that will require du to be equal to 9 secant squared 9x dx, which is fine for the first integral because we have secant squared 9x over there, so we're good there. So this will just be the integral of 1/9 times u cubed du minus the integral of tangent cubed 9x dx, right? So you don't have a problem with the first term. It's going to be 1/9 u to the 4th over 4. So that would be tangent to the 4th 9x all over 4 minus integral of tangent cubed 9x dx. And I guess this is the problem now, evaluating this guy. And because I'm now because we are now out of time, so I'll just leave this guys to you. I'll set up this because that's the thing that you need to evaluate now. Muriel is correct. You can again do the same trick I did before. Write it as tangent 9x times tangent squared 9x dx, and then use the secant identity again. Because again, tangents alone are hard to manipulate. So that's why you want the secant to go with it. So you'll have here tangent 9x secant squared 9x minus tangent of 9x dx. Okay. So here you can let u, oops, I missed the grouping symbol. So here you can let u be equal to tangent 9x, right? As what we had before, though we had a higher power there. And then, so I guess you can evaluate that. Now for the second part, you'll have the integral of tangent 9x dx. You will use the formula for the integral of tangent x dx. I guess this is ln of, what's the formula? Do you guys remember? This is tangent of secant, I guess. Absolute value of secant x plus the arbitrary constant c. Let me check that. Integral of tangent is, yeah, ln of absolute value of secant. Muriel, that's for the integral of secant x. For the integral of tangent x, either this or negative ln of cosine x plus c. So either of these two things, okay? So don't worry, I'll write the rest of the solution properly for tangent to the 5th 9x before I upload this worksheet. But I guess that's it for powers of trigonometric functions. But keep on practicing because here you have a lot of things to do. Apply identities, then use substitution. There are some rare cases that you will need to use integration by parts for, especially for powers of secants and tangents that are not covered with the first two cases that we have outlined before. I mean, those cases wherein we have no hard guidelines. And powers of trig functions is important because if you go to section 8.3, remember there you are integrating square roots, and to get rid of the square roots, you use trigonometric substitution. So you turn everything into trigonometric functions. And there is a big chance there that you will encounter powers of trig functions. So this particular topic can be embedded or can be required for some problems from section 8.3. So you see now this is like a chain. So for powers of trig functions, you might need IBP. Then for algebraic for trigonometric substitution, you might need some powers of trig functions. So it's very important that you be proficient in these methods before proceeding to the next. All right. So sorry for taking 5 times more than what is scheduled, but I hope this is good. Let me know on Friday if you still have some questions about powers of trigs. So try the exercises. That will help you a lot, especially in recalling the trigonometric identities, right? But, oh, it's already Friday. So let's meet again on Monday. So have a nice weekend, everybody, and hope to get some questions from you. Bye.